This is a simple rocket built out of a match head wrapped in aluminum foil, and as we put the flame underneath, it ignites with fast exhaust. The exhaust builds very fast. In a fraction of a second, the rocket goes the other way, and then you can actually see flames in the exhaust from this very simple rocket. And we got a bonus here as shrapnel from the inside comes out on fire and goes and lands on the launch pad dancing across. That's why I say that these can be a little dangerous and you should be careful. This attempt was really cool. As the rocket builds in temperature and the ignition begins to happen, it launches as usual. But watch carefully as this thing lifts off of the launch pad, you can see a spiraling bundle of flame, which is actually part of the match head tumbling out of the back. When you slow everything down and see how the flame and the shrapnel tumbles, it looks, in my opinion, absolutely incredible. In fact, even the smoke looks cool. That was actually so cool that I wanted to zoom in a little bit more and get up close and personal. Look how the tumbling match head is throwing off fragments that are on fire as it arcs across the table. Let's take a look at a slow motion shot of the fuel itself, the match head burning. Take a look at the lower left-hand corner and it really looks like rocket exhaust. And the actual match head itself seems to explode from the inside out. Also, pay attention to the glistening surface that sort of moves around. I think that's actually water being driven out of the wood and the cellulose there and being driven out onto the surface. And it really dances around and bubbles the entire time. This type of shot is why I bought the high-speed camera and why I wanted to shoot match heads anyway. I'd love for you to let me know what you really think. Let's push in a little bit and zoom in before ignition. Take a look at the water kind of glistening and dancing and bubbling. And then the ignition happens, and once it happens, boy, does it go. It really explodes from the inside out. And if you look closely, you can see sort of debris and shrapnel from the match head itself just literally flying out, almost like a deep space launch of a rocket engine. I also think it's fascinating to look at the boundary between the burned and the unburned part of the match head. It's almost like an advancing flame front in like a forest fire or a wildfire. And after the burning is over, because everything is so hot, the water that was beginning to come out really comes alive and bubbles and dances. I got really lucky on this shot. Take a look at where the flame is touching the aluminum. You can see a puff of exhaust and sort of like the force swivels the entire structure to the left, and then when we launch off at an angle. This is kind of like an attitude thruster for a rocket that's operating on a spacecraft in space, right? It burned a little hole in the aluminum foil, forming a little nozzle, and we get a sideways force. Again, due to Newton's third law, every action has an equal and opposite reaction, and that sideways force turns the entire structure, and then finally we get enough force out of the back to launch it off in the new direction. Here's what happens when you don't wrap it tight enough. You get a lot of exhaust, a lot of smoke, but without it being wrapped tight, you don't actually have enough force for the rocket to lift off. So when you're building these things, you want to wrap the aluminum foil tight enough to confine the exhaust and make a nice plume for a lot of really good force. But you don't want to wrap it too tight, because if it's too tight, then it can't slip off of the bamboo skewer, and you really want to have a minimal amount of frictional force there so we can slide off freely. So there's a delicate balance there. There's a couple of things I really wanted to get across in the next shot. First, when this one launches, it goes straight and true in a perfectly straight direction, and you can actually see fire in the exhaust. Right about now, you can see the fire. And when I reset the shot again, I'm going to zoom into the fire because I want you to see that these little bitty rockets actually have exhaust in the form of smoke and also actually fire. So they really are behaving like an actual rocket engine. And then finally, what I'd like to redo is reset the shot again so that when you look at it, it's a tracking shot of the exhaust. We're going to look at the exhaust, and I want you to look at the velocity of the exhaust as the rocket is moving in one direction, how fast the rocket exhaust is coming out the rear end. Now check out this incredible footage of popping water balloons at 1500 frames per second. You can just see every droplet of water taking its own trajectory. And just for giggles, let's reverse time and let the water droplets come together opposite of gravity and reform the balloon. I want you to notice how the needle makes it all the way into this balloon before the balloon punctures. And when it does rupture, it rips around the entire circumference, kind of taking water with it and spraying it in all directions, as the water then continues under its own inertia, falling toward the ground. Now check this out. As we puncture the balloon from the bottom where the tension in the rubber is less, the needle goes all the way in, and surprisingly, the balloon doesn't rupture at all. In fact, I was quite surprised to pull the needle out, and then the balloon just squirted water in a continuous stream and did not rupture. So I then had to go around to the other side of the balloon near the midpoint and then pop it properly from the side. Here it is slowed down a little bit more. This is around 2,000 frames per second, and it really allows you to see the trajectory of each individual water droplet just moving almost like its own little universe under the force of gravity. And just because I think it's so cool, here it is sped up a little bit and in reverse order, almost like time is flowing backward. Here's an extreme close-up with a different lens of the puncture itself, and it really allows you just to see the ripples in the water as it almost sits under its own inertia before gravity has a time to take it and pull it down. And here's the last slow-mo shot of a balloon popping before we move on to actually trying to shoot arrows into the balloon to see what will happen there. I just can't get over how it looks like a totally different universe of activity and action when you slow time down. Now, the first time I shot the balloon, I tried to shoot it at the end, but the arrow itself isn't that sharp. So all that happened is the balloon started jiggling and oscillating and gyrating, which honestly looks kind of incredible. Now I'd like to take us a little closer to the point of impact, and let's really look at how the balloon responds as soon as the arrow hits it and bounces off. You can see from the point of impact that it compresses the rubber, which then bounces back and starts the oscillations. After gluing a needle at the end of the arrowhead, it made a clean insertion point and exit point with an incredible shot of this balloon disintegrating in slow motion. Unfortunately, I couldn't get it to go through the balloon without rupturing. I think the impact is just too violent and always rips the rubber. Here's an incredible shot showing the impact point, and we can see the rubber fracture all the way around, rip apart, and then the entire process happens in a fraction of a second. Here I shot it again in a little slower motion of 3,500 frames per second. You can really see the rubber snap at the impact point, dragging the water droplets around with it, flinging them around essentially, and then the bulk of the water in the inside is mostly unchanged and then falls down under gravity. Okay, here we go. You can see the brick going in circular motion. And again, I'm trying to burn a hole through the string, but right at the last minute, if you look at the end where the brick is actually tied to the string, it became untied, by total accident, and then the brick separates from the string. And notice at the point of separation that it's not curved. It goes in very, very close to a straight line. Now here I've added a straight line to show you how close the motion is to being straight. Of course, it is curved a little bit by gravity, so it's not a perfect straight line, but if you did this in outer space with no gravity, it would be exactly straight. Remember Newton, an object in motion will stay in motion unless acted upon by an outside force. Here it is a little bit more close up where you can see the string become untied and the brick flies off in a tangent line to the original circle of motion. Now there's so much to talk about here. At the surface level, we see that this paperclip has a lot of potential energy stored before it hits the surface. The act of it hitting the surface dislodges the two ends of the paperclip and allows it to rebound and act almost like a spring, which then propels the paperclip up in the air. Now, from a physics point of view, it's a really great introduction to the concept of potential energy before the impact being converted to kinetic energy, which is the energy of motion as it launches up into the air. And so this is the law of conservation of energy in action. But beyond that, believe it or not, this is a really good analogy for how things burn, how fire actually happens. So when you think about it, oxygen is surrounding everything on my desk here in the air. And of course, the paper is sitting on my desk. And of course, if I bring a flame to the paper, it'll burn with the oxygen in the air. What does this have to do with paper clips? Well, the act of bringing the flame next to the paper gives an initial amount of energy to the oxygen molecules in the air and also to the paper, and causes them to collide with a lot of energy. And so it overcomes what we call an energy barrier. You see, the oxygen in the air and the paper, the fuel that's on my desk, they want to combine and go into a lower energy state, releasing heat and light. We call that fire. This wants to happen. But the only way the process can happen is if I give it an initial amount of energy to sort of start this chemical chain reaction. Also, you can see it in these paper clips. There's a springiness there, and of course it wants to convert that potential energy to kinetic energy, but the only way it can happen is by giving it an initial jolt of energy, which starts the process by unhinging the two ends of the paper clip. Then the process can complete. This is very analogous to activation energy in chemical reactions, especially fire. You need to give it a little bit of energy to start the collisions with such energy to begin the reaction to rearrange the electrons. Once the fire begins, then the heat and the light that are already there continue the reaction, and so we say the whole thing catches on fire. Another thing I find fascinating here is that as the launch happens, you can see the ends of the paperclip wobbling back and forth at a resonant frequency, right? That depends on the mass of the paperclip and the length of the legs of the paperclip. So there's just a ton of different things that we can learn from something simple like a paperclip.
They obviously go every which direction, and they don't appear to be very stable. Let's do it again. As I just kind of like let them come out, I can see them bounce every which direction. Occasionally you can see one land on the edge and then bounce and then spin a little bit and then eventually tumble down and settle down into its final state. But in general, when you just drop coins, they are what we call not stable, right? So alternatively, I can take a coin and I can just kind of like drop it just by adding a little bit of rotation. Now I know what you're thinking. You're thinking, well, duh, we see that every day. But instead of just assuming, oh, that makes sense, that's normal, let's talk about why is that the case. It's because it's kind of weird.
Now, I think what's really interesting about this is if you just give a little bit of rotational motion, then the coin is obviously more unstable. It gets a little bit of stability, but eventually starts to wind down and rapidly bend over and start going for the surface there and eventually stopping. And as you give it more and more rotational motion, it's very clear that it gets more stable, sort of like a bicycle.
If you lift it up and just kind of let it go, totally unstable. If you give it a little bit of rotation, very, very stable. And it's a lot more pronounced if you spin the coin. If I spin the coin, then it can stay up very, very long time. Now, even though it looks like kind of a solid sphere when it's spinning, if you spin it fast enough, it kind of looks like a solid sphere, right? In reality, there's only one contact point at the bottom. At any point in time when this thing is spinning around, there's only one point or very few points at the bottom there if it's a little flat, where it's actually contacting the ground. But yet it's a lot more stable. In fact, so stable, if you're very quick, you can actually put several of these things in motion at the same time, and you can see that they're more or less stable. Why is a rotating object stable like that? Right? You've probably seen a gyroscope. One day I'll do a video just on a gyroscope, but a gyroscope is a spinning body that seems to be able to balance and resist the tendency to fall over just by nature of it spinning. And what's happening is we're heating the air underneath this moving member. As we heat the air, it wants to expand. So it pushes the bellows up, and then it pushes the crankshaft, the push rod here. There's two push rods, one on either side, and it's basically pushing it up and turning the wheel. But as the flexible member on the inside gets to the cold side, then it cools off. And that cooling off effect gets transferred again back to the air inside of there, and it tends to cool the air off. So the air inside tends to contract, and then the thing moves down again. As soon as the internal member gets to the bottom of the hot area inside, it gets hot again, and then it causes the air to expand, and the process repeats over and over again. Let's just take a couple of ice cubes and see if we can put them on. Now, it's a little tricky to get them to stay on there, but I haven't changed anything. I haven't increased the temperature of the water inside. I think you can see right away that just by cooling the top plate, we're able to get this thing to turn faster, right? And the reason is because when the expansion and contraction process is happening faster, when the internal member gets to the top, it's hitting a colder reservoir, which is causing the gas to contract faster and then start the process over again. All right, let's see if we can get our engine going here. Let's see if it's hot enough yet. So we'll kind of start the process. Now it's going to make some noise when I put the dry ice on top. Usually it likes to slide around and make noise. It's just the way it goes. Dry ice is frozen carbon dioxide. So what's going on is as it sublimates, it turns directly into gas, and then it starts to slide around on the surface wherever it is. Let me put some on this side. All right, we can see it moving much, much faster now. I think I missed one little spot. Need some ice right there. Let's let it finish doing its little jiggle. And so you can see it moving much, much, much more rapidly when we have a hot reservoir slightly below boiling and a cold reservoir 78 degrees below zero, right? Negative 195. And it boils away right away, but you can still get that plate very, very cold. So you can see this thing is really cooking now. Now what happened was that when I pour it on there, it gets so cold that it sort of seizes up. But then it kind of overcomes that, and you can just see, now as you can see, it's starting to seize up. So let's see what happens. This is kind of neat. I've never really done this before. So let's just let it kind of thaw out a little bit. Something in there is frozen up. Now, just for giggles, let's grab some dry ice, which is not quite as cold, but we can make a nice cloud. So let's drop it in there, something like that. And we'll pour some liquid nitrogen on top. And we can get a little effect there. So you can see this thing is really cooking now. Much, much, much faster than before. So 100 degrees on the bottom, negative 195 degrees on the top, and you can see it's really cooking now. All right, we have our superconductor nice and chilled, and what I'm going to do is drop the circular magnet on it again from a little bit higher up to force the magnetic field to go inside, and let's see what actually happens. And you can see in this case, the magnetic field is not repelled anymore. It found one of those defect zones, and the flux from this tiny little magnet is now pinned inside, and it really can't move. If you try to push it, you can get it to deflect. See how I'm pushing it left and right? I'm kind of pushing it back and forth. It's kind of going back to the same place. If you see it kind of going down to the surface, it just found a defect zone closer to the surface, right? If I physically bring the magnet close and force it and then just let it go, you'll see it'll levitate there. Now again, sometimes it's trying to repel the magnetic field. Depends on if it found one of those little defect zones inside here. And we'll go from there. So to do the levitation, I'm going to push it really close, force the field lines in, and then let it go. And you can see it's actually spinning very slightly there as well. I have some iron filings attached to the side of it. That's why you can see it spinning there from a previous experiment there, right? So it's not magic. What's really happening is the magnetic field is trapped inside the superconductor. So it initially doesn't want to let any in, but if any does get in through a defect zone or an imperfection, then the surrounding superconducting material generates eddy currents in the material that create a magnetic field that physically lock the flux lines from that magnet in place, and so it can't move. Now, if you push it hard enough, it'll move, but in general, if I give it a little nudge in either direction, it doesn't really want to move. All right, let me take that one out and do a little bit of a bigger magnet here. Let me add a little bit of coolant here. All right, here we go. So now what I'm going to do is I'm going to drop this thing from a height and see if I can get it to lock in place. Camera, I hope it looks really cool, but in person, it's just, it looks like magic. I can't even describe it with any other word other than that. It looks like magic, right? If you push it, you can get it to move, but it wants to spring back into place. The magnetic field lines from this magnet are locked into place. And in fact, I can physically move it and make it change orientation and make it lock in a different orientation. So I'll push it this way, for instance, and then I can see it locking like that, right? I can grab it and remove it, and then I can physically place it back and try to get the field lines to lock in place horizontally like this in a different orientation. If I apply a little force a little bit lower, it'll lock lower. If I try to tilt it up, it'll lock in a different orientation if I can get it to do it. They're kind of finicky. You get the idea. As I move it around, I can get it to lock in different orientations vertically. Now that was the circular magnet. Actually, I think the most impressive one are the square magnets that I have here. And the reason they're more impressive is just because you can see them spinning a little better. So here I have just another magnet, and this one is square. Let me see if I can get it to go perfectly horizontal. And of course I can't. All right, let me see if I can get it to lock in place perfectly horizontally. I got to push it kind of close and then let go. It's pretty close to horizontal, not perfect. You get the idea. I can kind of push it down a little bit and hopefully get it to get as flat as I can get it. That's pretty flat. All right, now you can see the levitation happening. If I give it a nudge, it's resisting me, right? It's resisting as I try to turn it, but if I really work hard, I can get it to spin. And you can see because of the corners how frictionless the whole process is happening. You can see it kind of back and forth, back and forth. That's because the flux is pinning and it's kind of like overcoming the flux pinning in place there. All right, now what I have is a donut magnet, and what I'll do, I can feel the repulsion happening as I bring it down on top, right? But what I'll do is force the field lines into the superconductor, force it to be pinned, and when I feel like I've got it, I can lift the whole thing up, and it will be suspended underneath the magnet here. So now what we have is a track made of magnets, and I bet you can guess what's going to happen next. If we're careful, we should be able to levitate this thing pretty far above this track of magnets. Let me get it nice and cold, right above the track, and let go. Oh, look at that. You can just push it all the way around in a circle. And check this out. You can get it to pin in different orientations. As I move it, you know, I can go down closer to the track. I can try to pull it up from the track. And what we can do is we can pin it in place, flip the track upside down, and we can actually have it suspended underneath the track.
Learn anything at mathandscience.com.